Welcome everybody. It's a pleasure to be here today. My name is Monperrus. I'm from the University of Vrije, and I really appreciate the invitation of Francis and his team to give this talk today on antifragile software. And I will, if you don't know already what antifragile is, I will present it. Let's, for the moment, keep the surprise. Let's start with a very concrete example, which is slide number 2, a wonderful picture of Sylvestre Jean Didier Monperrus, my son, born on May the 18th this year. And Sylvestre has the ability of being very, very calm as this day, just probably 1 day or 2 days after he was born. But yesterday afternoon, he was not calm at all, and I was responsible for looking after him. Because my wife gave a course, so I had to look after him, and it was, so my wife gave a course at the University of Vrije as well, so she went to the University of Vrije with Sylvestre, and she gave Sylvestre to me, so I had to look after him. And unfortunately, currently my office is being renewed at the university, so I have one room, but it's completely empty, no desk, nothing at all, very dirty because I just did the painting. And also yesterday afternoon, I didn't have my plug to charge my battery, which means that basically I had a presentation to prepare for today with one kid crying, no office, and only a few hours of battery, so not enough for doing the result. So, which means 3 factors of stress. 3 problems with respect to preparing this talk. And what's antifragile is that even if a system is antifragile, if it becomes better with the presence of stressors and problems. So in that sense, my talk would be antifragile if it's better today because of the problems I had yesterday in preparing it. I don't know, you're the only judge of this. So this is the definition of antifragile, invented by an American essayist called Nassim Taleb. In one slide, it's a system or phenomenon which is better with the presence of stressors, shocks, volatility, noise, mistakes, faults, attacks, failures. They all refer to this notion of it's not a normal expected input or characterization of the system. So this is antifragile. So it's the name has been invented by Taleb. It's in a book he published 3 years ago, and in this book he discusses about the concept. He gives many examples, in particular in the finance domain, because he has been a trader for more than 20 years. And so for him, the key word here is volatility, because a market is volatile, which means that it goes up and down. And for a trader, what's really good is that you win money whether the market goes up or it goes down. And what's even better, if the market goes really high and really low in a very short period of time, you make more money. Which means you in this case, the term better would mean you win more money. So the more noise there is in the market, the more money you make. So he gives many examples in this book. Other examples, such as in biology. So, for instance, the immune system is antifragile because it gets better when it's constantly exercised by microbes and viruses in your environment. If you don't have microbes and viruses in your environment, your immune system is getting worse. But in his book, Taleb doesn't talk at all about engineering, or a little bit, but not really, and he doesn't know anything about software, which means that there is some work to do to apply this antifragile view to software. And so to build what would be anti-fragile software. And what's interesting is that stressors, shocks, volatility, noise, somehow we have quite easily a good picture of the error models of software. What they are, it's attacks, so attacks from hackers, for instance. They constantly push the software systems. There are bugs, so bugs are noise from the inside of the software systems. There are change in the requirements. In real life, the expected functionalities of the software system are constantly changing, up to several times a month. If you want to follow, I don't know, an innovation, or you want to provide a new functionality because of an event in the news. So they are the stressors of software. So basically, we know we have a clear view of the stressors of software, and now we have to ask, okay, what does it mean to get software better from those stressors and problems? But before doing this, let's ask, okay, is software fragile? If we have this anti-fragile, is software fragile? And the answer is not easy, but again, we have many examples, such as 1 year ago, more than 1 year ago, in December 2013, I was working and I wanted to check out some code from my students. And so I started my development environment, so launched it, and then it crashed. Why does it crash? I started again because a reboot is the best solution for problems, and it crashed again. So I had no way this particular day to start my development environment. 1 week later, so I googled the error message, nothing. 1 week later, I googled again the error message. At some point, I realized that okay, there's probably a problem with the browser of the development environment. So there is a browser embedded into the development environment, but nothing complete. And 1 week later, I had a Nokia conference for European project, which was on Google Hangouts. So I tried to connect to Google Hangout, and then I noticed that there is again the same crash. What happened? And by Googling again, I realized that actually, so the development environment tries to load a browser for just browsing the documentation, and that the browser tries to load a plugin for a Google Talk. And a crash in the plugin of Google Talk was propagated to a crash to the browser component of the development environment, which was itself propagated to the crash of the development environment, which is bad, and which is indeed very fragile. Why? Because the Google Talk plugin is an option for a browser. You should be able to browse without the Google Talk plugin. And also, the browser, so an HTML rendering engine, is also an option for the development environment. So there were absolutely no reason for the browser to crash, for my development environment to crash because of this Google Talk plugin. This is an example of software fragility. And actually, if you use software, as we all do, if you develop software, we have all examples of huge problems due to special cases and communities. So software is indeed fragile, and even if there are many works on creating the software more robust, we are not yet to anti-fragile. So, but what would it mean to have an anti-fragile software system, or an anti-fragile development environment with respect to this particular crash? Because a robust one is pretty clear. It's that there would be the crash in the Google Talk plugin, but not the crash in the development environment. It may mean that you can imagine a system in your IDE that automatically installs different plugins. who don't necessarily use them, but they install different plugins. And the software system would also observe whether the development environment starts or not. So it would explore somehow the set of all possible combinations of plugins. And at some point, there would be on one user the same crash as I had on my machine. Because this user would have also this browser configuration and this Google Talk plugin and so on. But what would be the difference with my case? In my case, I had a crash and absolutely no solution to do whatsoever to start to work. And if it would have been mission critical for me to start this development environment, it would have been terrible. But if you have a system which constantly installs one plugin or another plugin, or try different combination, when the crash happens, the system will monitor the occurrence of the crash, would disable the plugin that has just been installed, and would report to the Google engineers, there is an error propagation between this Google Talk plugin and the development environment Eclipse, which is the problem. So this starts to be, this gives the first intuition of more clearly what would be anti-fragile software. It would be introducing some noise, but getting some concrete engineering information about this noise. So in this case, the noise would be installing random plugins in your browser. But the gain is that the crash would have happened only once to a machine. The next restart would have worked because the system would have disabled the user's plugin, and the error would have been reported to the Google engineer. So basically, we have three things. We have the perturbation model. So in the case of my talk, the perturbation model was having one baby plus an empty office plus no battery. It's having a clear perturbation cost. So in my case, it was the stress I had yesterday evening. This morning, I was terrible with my wife and kids this morning because I was too stressed with this talk. And it's also having a perturbation gain. The gain, in a pure anti-fragile way, it would be a better talk today. In the example of the Google Talk plugin, the gain is that nobody would have suffered from the crash as I suffered, and the error would have been reported to the developers. So we really have this perturbation model, perturbation cost, and perturbation gain. Before going further, let's go to my daily job. So I'm with the University of Lille, and my field of research is software engineering. And within software engineering, my expertise is automatic repair, automatic bug repair. So what we do is that we build systems which take bugs as input and produce solutions as output. So for instance, a solution might be a patch. So the patch might be, okay, if you add if x higher than 10 before a statement, the bug is not there anymore. This is a complete source code patch. But it could also be something else. Sometimes the patch is not on the code, but at runtime, on the system state. So you slightly change the system state at runtime to get a solution. And this is the example of le Château Saint-Jean de Nogent-le-Rotrou. So Nogent-le-Rotrou is a wonderful city, and it has a wonderful chateau. So Nogent-le-Rotrou, it's in the western part of France, between Chartres and Le Mans. So Chartres, it's a nice city because it's where the cathedral of Chartres is, the most beautiful cathedral in the world, according to Taleb, and also according to me, because I grew up in Chartres, actually. So Chartres, there is a wonderful cathedral, and at the west of Chartres there is Nogent-le-Rotrou, and in Nogent-le-Rotrou there is a castle here, which is a typical example of robustness engineering. The dungeon here, the walls of the dungeon are 3.5 meters wide. They are a typical example of robustness. But the problem with typical robustness is what happens if the bug is inside the dungeon. It's a little bit like software, so robustness is also always about outside, but what happens if the problem is inside? But more than this, the thing with Northern Road is that it's a favorite city of John Knight. John Knight, a researcher from the University of Virginia. And John Knight has invented something very interesting in the 1988 called data diversity. The key idea of data diversity is to build a system that is resilient to bugs. And how does it work? Basically, the system should return function of an input. And for a certain input, you have a crash. You have a problem. And the idea of data diversity is that you slightly change the input, and by slightly changing the input, you don't trigger the crash anymore. Of course, you will get a different output, but the output should probably be close to the initial one, to the expected one. So in this case, we change the system state, and by changing the system state, we get an output which is acceptable for the system under consideration, which is data diversity. And in data diversity, there are two key insights related to antifragility. The first one is that indeed this can be seen as noise. So by adding some noise in the system, in the input, we get robustness and even resilience because we replace crashes by outputs. So this is the first thing. So, okay, noise, we gain something by adding some noise. And the second thing is that we have this notion of acceptable result. So the result of f of input plus delta is not the same one as the initial one, but it's still acceptable. And this notion of acceptability is extremely important for software repair and for antifragile software. Because basically for software repair, we are dealing with real software systems and we are never sure that the change in the system is perfectly correct. But what matters is that the change in the system gives you an acceptable result, an acceptable output. And for antifragile software, the noise you add in the software system will have an impact, and it should remain acceptable. So in both cases, we are based on this notion of acceptability envelope, or acceptability-oriented computing, a concept explored in particular by Martin Reinhold at MIT, where we don't consider software as something that is correct or incorrect, what I call binary correctness. In this case, we consider software as something that produces an output, a behavior, and this behavior should be acceptable. And somehow the surface of this acceptable behavior is quite large, and instead of just having one point in this software, we can have many points. And again, with respect to antifragile software, by adding some noise in the process, we stick into the acceptability envelope the set of all possible acceptable behavior. So now we have the link with acceptability and repair and antifragile software. But we have something more, which is this. Basically, in software repair, the key insight is that it's impossible to have 0 bugs in production. Because the systems we build are too complex, so there will be bugs in production. And if it's impossible, it means that it's impossible to test the all possible state of the software system, and to be sure that for all possible states it works. This is the notion of state space. So for the software systems we have today, the state space is incredibly large. And we also have the error space. So for each point in the state space, there are possible errors which slightly change and which would have some impact on the rest of the system. And basically, what in antifragile software we replace when we add noise, instead of only exploring one state in production, we explore points in the neighborhood of the system state to see whether it still works. So if I come back to the example of the Google Talk plugin, by randomly installing and removing browser plugins, and each time I start my development environment, I don't start on the same system, on the same point in the system space, but on different ones. And by doing this in production, instead of trying to explore all possible points at testing time with only a small testing team, it's the users themselves that explore all possible points. So we transform the software execution from exploring only one point to a set of points. And in particular, we explore the points where we are in an error mode. We explore them before they happen. So we explore them proactively. Again, with the Google Talk plugin, the difference between what happened to me in December, which was a crash and the complete, and it was impossible to use my development environment for 2 weeks, it would have been replacing this huge problem with a small one where it would have been only one crash on one machine, because one machine would have explored this particular bug, and so the crash wouldn't have happened for me. So we have this formula, and this formula also makes a key difference between what my work on software repair and antifragile software is that software repair, it's a purely reactive activity. We wait for bugs to happen. On the contrary, antifragile software, it's really a proactive activity. You always trigger bugs, you always trigger problems because when you trigger them, so first you have a complete control of what happens. So again, with the Google Talk plugin, the monitoring system would notice a crash with Google Talk and just after undo installation, so uninstall the Google Talk plugin. So you have a complete control. And since you have a complete control, you can mitigate the propagation of the error very fast. So by exploring this proactively, this space, you have this control and this possibility to mitigate the errors. So now let's go to concrete examples of antifragile software. The first one is something very interesting called chaos engineering, recently called chaos engineering, with a very nice web page, principlesofchaos.org, which is, so this has been invented by an American company called Netflix. Quite known in Europe now because they are known in Europe. And Netflix, what they did a couple of years ago is they invented a system called the Simian Army. What's the Simian Army? It's a set of monkeys. And what's a monkey? A monkey is something that let's say, that is involved into the execution of the software system and that do something randomly. For instance, the chaos monkey. The chaos monkey for Netflix is a monkey that randomly shuts down servers in production. Netflix, as all software companies, their production consists of hundreds, thousands of servers. And when you watch a movie on Netflix, there are many servers involved. And sometimes the chaos monkey shuts down randomly one server. So it's not one server that is useless, it's one server that is involved into the production system, but they shut down it. And why do they do this? They do this because they want to be sure that their global system is resistant to server shutdown, because there can be server shutdowns due to hardware problems, power errors, and so on. So in this case, we have again the perturbation model. It's quite clear. It's shutting down servers. The perturbation cost is that this will have an impact on some users, but the user should either have a fallback or click on reload, or there will be just a lag of 2 seconds before the traffic being routed to another server or whatever. There is a perturbation cost. And there is a perturbation gain, which is pretty clear. It's that they constantly prove that the system is resilient to arbitrary server shutdown. And so this was called the Simian army, and now this is called chaos engineering. So they have reworked the terminology, and I said proving that the system is capable of resisting to server shutdown, because it's actually it's really something scientific in terms of scientific method. Basically, what they do in chaos engineering is that you first state an hypothesis. The hypothesis is Netflix. The service of Netflix should not be degraded by the server shutdown. This is the hypothesis. And so you have a perturbation, and you have a measure. So, for instance, the measure is the average latency of users. So you have an hypothesis. It's exactly as a scientific hypothesis. Then you are in production. So you have this while true loop. You are in production, and at some point you perturb the system. So you shut down the system. And if the measure is unacceptable, so which means that, for instance, there is one user which has a huge lag, you report a failure. So in this case, you don't report an actual failure. You have proven that the system is not capable of being resilient to this perturbation error. So this is chaos engineering, and this is purely antifragility. This is purely antifragility. And they use this in production, and they are not the only one. Another example of antifragile software can be found as early as 1975 in a paper called Design of Self-Checking Software. And in this paper, page 4, the authors start to discuss about an air traffic control system. So something very common in the software engineering literature. So a system that controls the planes landing and taking off and so on. And they say that the system should be able to accommodate for ghost planes. What are ghost planes? It's fake planes that only exist in the software system. They don't exist in reality. But the software system should be able to handle them with no problem. And again, here we are, this is antifragile. Because the perturbation model is having arbitrary ghost planes in the system, and the real plane should still be able to land safely and to take off safely. So this is typically antifragility. And what's interesting in this second example as opposed to the first one is that in this example, the measure involves humans. Because in air traffic control system, you have also human operators in the loop. And somehow, in this ghost plane example, the perturbation model also exercises the recovery capabilities of humans. So basically, if all planes can land and take off safely, it means that, okay, the air traffic control system, software system is working fine, but also it's that the interactions with the human operators are fine, and the human operators are doing their job well. So you even prove the capability of the whole socio-technical system to be resilient to the failure.
Do the humans know that there is a ghost plane?
To my knowledge, ghost planes have never been implemented in production.
Okay, it's just done as an exercise.
It's an idea. But I think it should be. So these are two examples of antifragile software. So now I think we have a better understanding of what is antifragile software. Now, how to build antifragile software.
Can I ask a question?
Yeah, of course.
So, I guess the system, how does the system learn if it doesn't fail? In this case, for example. If this
you always have a measure here,
yeah,
which is the observation you want to make on the system. So in the case of Netflix, the observation is the number of dropped requests or the latency of...
okay, so this kind of, you can optimize it for latency. Even if it doesn't fail, if the measure acceptable, you can sort of still minimize it.
You see, you never minimize it because you have a basic latency, and when you shut down servers, it will increase. It has to increase. But in the acceptability envelope, so within an acceptable range.
Yeah, okay, I'm just thinking how does it learn without failure? So let's say with these planes, ghost planes, if I sort of put ghost planes into the system, and if it works fine, then I don't change the system because it's kind of good enough.
You don't change the system.
So I change the system only when it fails, but this is sort of unacceptable failure, at least with planes. So you don't do this in production. Basically, you cannot do it in principle this in production.
The thing is the only way to know in production that the system is capable to resist such events is to have ghost planes. The question you ask is how you integrate at the beginning, how you integrate ghost planes in the process. So because basically what you mean, if I understand what you mean, is that you cannot afford for an air traffic control system, you cannot afford a crash, a plane crash for sure. But by doing this, you can detect, for instance, delays, very problematic delays in landing and taking off. So this would be a problem, and you could solve this problem and continue to exercise the system with the ghost planes.
Mm-hmm.
And in this ghost plane example, the key assumption is that if you don't do this, and this is so if you don't have ghost planes, so you only rely on the classical engineering techniques, but you are never sure. You're never sure that you don't exercise the resilience capabilities of the system. And hopefully by having those planes, you would have small failures, like a delay, instead of catastrophic events like a crash. And in this case, we find again one way of presenting antifragility by Calais, which is it replaces catastrophes by small errors. And so ghost planes will replace crashes by delays. In the example of the Google Talk plugin, we would replace the impossibility to use the environment for 2 weeks by one single crash, and so on. So now we have a better idea of what's antifragile, what would be antifragile software. This already exists, for instance, at Netflix. Now the question is how to build antifragile software. And for this, so this is not a classical area of research. There is very, very few things. So these are all only speculative proposals. So the first one is fault injection in production, which is this chaos monkey, for instance, where they shut down servers. And so fault injection in production is definitely one way of creating antifragile software. For doing fault injection in production, it has to we have to change the way we engineer our system, because basically we need to embed in production a fault injection library. So how we need to add new requirements in the software system, which are the system should constantly explore its resilience capability. So this engineering concern, so this is an engineering concern which today doesn't exist at all. Really But this engineering concern is new, so it should be integrated into the whole engineering process. So we need libraries, software libraries, and so on for doing this. The thing I'm seeing is that this notion of antifragile software and noise, it has to do with randomization. And today, the software stack we have built over the last 40 or 50 years, it's pretty much deterministic at all levels of the stack. And this is problematic because, for instance, for years, many attackers, many hackers, were capable of attacking software systems because they knew that the memory layout would start at memory address 0, and the code segment would start at memory address 100, and the data segment would start at memory address 1000. So they would just, from the output, try to inject one piece of malicious code at address 344, and it would work, because it was completely deterministic. And then we invented something called address space layout randomization, so ASLR. And now ASLR is embedded in all production systems, Windows, Mac, Linux, and so on. And basically what ASLR does is that we never know in advance what will be the start address of the system. It's randomly taken, and then the program is capable of running because it's only neutral. So if you know the start address, you do plus or minus the start address, and you find the same value. So when we introduced ASLR, we introduced some noise in the software execution. What was the cost? The cost that many existing programs were broken because they expected some particular addresses that were hard-coded somewhere in the code. So it had a cost at the beginning. But what was the gain? The gain is that by only doing this change, we completely removed the full class of attacks related to the exact memory layout. And my deep belief is that in the software stack we have, and when I say stack, if you are not, and for some of you are not software engineers, but a software stack, if you represent it as a pile of engineering decisions, it's millions of engineering decisions one on top of the other. Literally millions. And my point is that in all those engineering decisions, many of them are deterministic as the memory layout before, but should not be. There should be one component, one randomization component of this thing. And I'm sure that we can find many places in the software stack where we can inject randomization as we did for memory layout. And by doing this, of course, we have an execution which is much less deterministic, much more noise during the execution. So it's almost volatility in the market sense of Fragile, but we would build much more resilient software systems. The third point here, it's again the point with ghost planes, is that all real software systems they interact with humans. And somehow we need to explore the antifragile aspect of humans, of the human factors, which means that, which means many things. For instance, if the perturbation model is that an operator can make an error, a human error, a configuration error, this happens, and many problems in reality are due to human errors, then it would mean that at some point you would ask operators to deliberately do the wrong decision in production. So ask the air traffic controller to wrongly route the airplane. They say, okay, cool, click on the red button and not on the green one. Another way of putting this even further is that maybe we should always keep very bad human operators in the system Because they constantly exercise the capability of the system to resist to human errors. Which means we should always employ purposefully bad people. Or maybe we, as humans, you could specialize as being a bad human operator. Employ me because I will make
Gaston Lagaffe.
Exactly, Gaston Lagaffe. Very typical Antifragile example. Gaston Lagaffe is typical.
Gaston Lagaffe.
Exactly. Gaston Lagaffe. Yeah, but yeah.
I have heard you already mention several times that you have to inject faults in production, that you have to do things in production. Why is it so important to do it in production? Wouldn't this work in a controlled setting as well?
Okay, for two reasons. So first, of course, you can do it at development time and testing time. And you can, and it's a very good way to do it. But again, for software systems, it's impossible to explore the space of possible behaviors, the space of possible system states at testing time. You will need an infinite amount of resources, but you don't have. So you do all the classical engineering stuff at development and testing time. I'm not saying that we should replace the classical engineering stuff. We can augment it at testing time with fault injection too. But when we cross the boundary of production, we should continue to inject faults. It's in my point.
Yes, it should be also in production.
Also in production, and fault injection actually it's also in production. But it's not. It's a little bit anti-fragile before, but it's not really in the vision of. And the fourth point here is very important. I think it's education, because nobody knows for sure what are the reasons of the fragilities we observe today in software systems. It's really hard to tell this or to design experiments. I tend to think that one of the causes is that we have been taught for decades as software engineers with the wrong mindset. We have been taught with this notion of binary correctness. It's either correct or incorrect. We have been taught in this notion of determinism. Your program is not deterministic, this is terrible. This is also bad. So because of this is why we have built those software stacks with absolutely no randomization at all. So probably that if we change the way we teach students in the universities, they would start to think in another way, and they would start to design their systems in another way so that they would become less fragile, and with the rest, they would become anti-fragile. But at some point, for sure, we have to change the mindset, the complete mindset of thinking. So we arrived to the end of this talk. So basically, this notion of anti-fragile software and maybe anti-fragile software engineering, it boils down to those 4 points where we need perturbation models and very clear and principled perturbation models. So it could be, again, so the perturbation model could be randomly installing plugins in a browser, it could be randomly shutting down servers, it could be always keep 1 out of 10 human operators really bad and not trained. But we need a perturbation model. We need a perturbation controller. So what's a perturbation controller? In this example of Netflix, so where they shut down servers, they only shut down servers on business hours. Because if something goes wrong, they want their engineers to be able to fix that problem. For ghost planes, we may only inject ghost planes in small airports or at time where the traffic only has cargo planes or something like this. But we can really control the perturbations also in a very principled way. We always need also the cost of a perturbation and the gain of a perturbation, because the key thing is still engineering. The key thing is that the cost should be lower in the game. Because we don't want to inject noise for noise, we want to inject noise for obtaining something. So in the example of Netflix, the cost is to have a slightly worse service, but the gain is that at Netflix, they are 100% sure that many servers can crash. Nothing would happen on the service side from the point of view of using. And at Netflix, they do something even better, so it's pretty good to shut down servers. But they also have another perturbation model, which is called the chaos gorilla. Not the chaos monkey, but the chaos gorilla. And what's the chaos gorilla? It's not shutting down one server, it's shutting down a complete data center. Because they know on Netflix that at some point, the data center of Amazon in Ireland will crash. It has crashed in the past, and it will crash again for some reason at some point. And they want a service, so their hypothesis is that their service is capable of resisting to this error. And the only way of always exercising the resilience code and proving that this is the case is that regularly the chaos gorilla comes and cut all connections between a complete data center. All the traffic has to be rerouted to another data center in the US or somewhere else. There will be an impact on the service at the end. You will notice as usual that Netflix is slower now, but it will still be usable. And they will still make money with the service, and they wouldn't suffer too much from this. So in this case, they really made a very strong resilience hypothesis. And this is the end of my talk. I really thank you for your attention.
The controller works at another level of abstraction because it has to deal with noise, it has to automate, it has to, no? And yes,
Okay.
the perturbation controller works at another level of abstraction because it has to introduce the noise.
Yeah, exactly. You can do this. It's one component in the system, which is a kind of meta, or at least it's not a functional component. And it has to interact with the rest of the system as other non-functional components.
How do you measure the perturbation gain? Because in some of your examples, I kind of understand that you measure the gain between the crashed system, which is what would happen with your Eclipse, with your ID example, and the non-crashing system, which has degraded operation. But then when I think about your other examples of antifragile systems, for example, biological, when you're exposed to viruses and stuff like that, when you get a vaccine, you get a reduced version of the virus, but then you become better than what the perturbation was. So there the gain would be measured against your healthy self before the vaccination and after. So it's not so clear to me how you measure the gain of the system after the perturbation.
It's really hard, for sure. But going back to the example of vaccines, the thing is that you can say that okay, your immune system is better after, but actually what a vaccine does is that after the vaccine, you are capable of resisting to this virus. And it's almost the same thing with the Netflix example. By doing this, the system is capable of resisting to virus. And you know that it's capable of resisting to virus. It's even better, Netflix is even better than the vaccine, because the best vaccine would be that you are first getting vaccine, and then you will be exposed to actually the virus to see whether the vaccine has worked. But this is somehow maybe what we do when we have sometimes it's done in 2 or 3 ways, and maybe this is actually what the doctors do. But in both cases, the net result is that you are capable of resisting. And in general, measuring the gain is extremely hard, especially since, in many cases, for antifragile software, we prevent ourselves against events that have never occurred so far. So we are not capable of telling the exact cost of this event. We can vaguely estimate it, but we cannot say it could be $1 million. We just don't know.
I think the gains are pretty clear, at least in the case of servers. Then you know that your system can...
Yeah, my question was more towards, okay, you know that there is a gain, but are you comparing the gain between the functioning system and the system after perturbation, or between a crashed system and the system after the perturbation? So, of course, almost anything is better than a crashed system, right? But maybe it's not worth it for me to go perturbing the model and doing stuff if the system is going to be only marginally better than if I just leave it alone. You see what I mean? It depends on how you measure it.
But I think actually you will measure it over time. You will somehow integrate it over time. Again, the thing is that theoretically, the cost over time is the sum of the cost of all the small errors due to perturbation, let's say, in nodes, against the cost of one catastrophe that will happen after, I don't know, 1 year, 10 years, 100 years, you don't know. But this is the actual cost you compare against.
I think you should measure the gain in the increase in resilience. If you could somehow measure the resilience of the system after the perturbation has taken place and you found out that with this correction it will survive this perturbation, you have increased the resilience of the system. So if you could have some kind of a measure of resilience, that would be your measure of perturbation gain.
And the cost would be the distance between the acceptability obtained and the expected
Exactly.
behavior.
Yeah, you can put it this way. The cost in this case would be exactly the distance between the nominal behavior and where you are in the acceptability on that. Yeah, definitely. And in some cases, you can really measure the cost and also the gain, because, so for instance, if you inject faults into an e-commerce system, you can know almost precisely how many orders are completely cancelled because of the fault. So you know that if without fault you would have you would have a $10 basket being ordered, or so in some cases you can really measure the cost, and you can also really measure the gain, or at least do a simulation of the gain, because if you assume that at some point there is one data center being closed, and you know that for 1 hour, and you know that the typical business hour in your e-commerce website is $1 million, then you can really compare. You can really compare this nominal loss against the small loss we have. So, in some cases, and it's possible to do it, and I think it's possible in many cases, but it's probably one of the hardest. This one is the hardest point, because again, the perturbation model, as I said in my beginning slide, for errors, it takes us 1 minute to say what are the possible perturbations by changing in the
I'm not so sure it's easy to make a perturbation model, because as you say, the state space is typically infinite. How do you sample that?
I agree, but having the very good answer takes time, but having a first answer is really can be done within minutes, I would say, for a perturbation model. Same thing with the perturbation controller. When we say that we shut down servers during business hours, it's not rocket science. The cost is harder, and the gain is really the hardest part in this engineering.
Cost, I think, is relatively easy to calculate, because you know
exactly what.
Yes.
Yeah.
I think the perturbation model and the perturbation gain are the most difficult ones.
Yeah.
Well, gain is sort of related to cost, I guess.
Yeah, but if you have the one, you don't necessarily have the other. So they are related, yes. But,
No, you can have the cost without having the gain.
exactly.
I mean, you can
In most
test,
cases, you have the
you can test things and never find any problem.
Exactly.
And then, well, what's your gain except that you are more confident?
Exactly.
Create problems because here you inject fault also. So if you
No, if you find the fault and then you correct it, then you have made a gain. And if you don't find the fault, then maybe you're just wasting your time trying to create fault data and then.
Yeah, maybe.
I'm still a little bit confused about the notion of anti-fragile systems. So, in essence, if I understand it correctly, an anti-fragile system is a system which becomes better due to stresses, right? But then, depending on how wide you define a system to be, you could say that every successful system is, a long-lived successful system is by definition anti-fragile, exactly because it has survived the changes.
Exactly.
So then you would have to say,
That's the key point, that the best fault injector in production is time. Time is the best thing. So I used to be a paraglider pilot. And my paraglider instructor was also a plane pilot. Always said that there is no good pilot, there are only odd pilots, which means that only time can prove can the control is good. And again, because you in nature we have natural force constantly, natural changing conditions, and so somehow it's a perfect fault injector, but it necessitates time. If you don't have this time, if you want to build a really strong system, a resilient system up front, we need to simulate time. And somehow we can see the perturbation model and controller as a way to simulate time.
Yeah, you speed up the number of problems that would normally
Yes. And you speed up by orders of magnitude.
But I still don't think that this is actually a model of anti-fragility. This looks more like a model of testing, because the system will not in itself improve by the mistakes that you inject. You have to improve it afterwards. So a true anti-fragile system would learn on its own and would become stronger on its own.
Well, again, this when I say this, when I put this because this is something that is actually absolutely not done today in classical engineering. And this is definitely one part of antifragility.
I think it, well, maybe not in software engineering, but I'm pretty sure that in other domains of engineering they have similar
In
methods.
production? In production?
Yeah. What about limitation testing?
It's not in production
It's-
again.
Okay,
Again.
it's not in production. What about machine learning requires negative examples? You don't need only positive examples, you need negative examples in order to train your neural network.
Also good, but it's not in production itself.
Maybe no, that's not really pertinent.
Yeah, but something that I actually I am really perturbed about the perturbation model actually is because the perturbation model means that if you have one, you can predict what can go wrong, and sometimes you cannot predict. You have an anticipated stuff problems. I don't know when.
This is actually the point here.
Yeah. So sometimes how could you manage an anticipated change or an anticipated interaction that is not in the perturbation model?
The thing is that this is the whole point somehow of the perturbation controller, is that since you are doing proactively, you are using the perturbation proactively, you are somehow able to control the propagation of the effects, to mitigate, to stop, to roll back, and even if it goes really wrong, you are able to control the stuff because you are because you do it on purpose, as opposed to just waiting for the natural faults to happen, but you don't know when they happen, and you are not ready when they happen because nothing is set to mitigate and to control. So you see the whole point of doing this in proactive manner and in controlled manner is that you put everything in place so that if something unanticipated happens, you are ready to handle it.
if an unanticipated reaction to the anticipated perturbation. Because Netflix has to know that a server is going down is a potential problem.
Exactly.
There are things they don't know, they don't know.
Exactly.
Yeah.
That's why it's
That the server doesn't go down, but starts sending signals in a strange way with kind of short interruptions, and it's not down, but it's not functioning normally either.
I agree. That's why again, it's really scientific. You always know with respect to your hypothesis, not more, not less. But the interesting thing is that what matters, and it's really clear in this web page, in principlesofchaos.org, is that what matters is not the root cause. What matters is the actual effect. So, because when we shut down servers, actually we don't say whether we are injecting a fault on the hardware side or on the software side or whatever. It don't really matter. We don't do any hypothesis on the root cause of the server being shut down. Or maybe it's a terrorist attack on the data center. We don't care. We know that it's the server or the data center that can shut down. And what matters is the effect and the end-to-end service. So somehow we abstract over the concrete cases, we abstract over the anticipation completely, and whatever would result in a server shutdown will be handled by the system. You can rephrase it this way.
How would that script be different from the one I would use to test a system? I have a hypothesis, I have a series of tests, and then I have expected results, and while true, I test, and if the expected result is not there, then I say,
No, the difference with testing is while true. In testing, you don't have an infinite resource. You say, while I spend 2 months of testing, so most of the work, and if testing is not efficient, the perturbation would not be realistic, and you wouldn't find the errors you would look for.
Is this a while like a metaphorical while? Like it should be constantly doing this, or is this like a continuous while? Because testing is something that you're supposed to do all the time.
It's the first one because it's again it has a cost. So in testing or in production, it has a cost. So again, so to me, this is the same thing as testing. The only thing is the two differences with testing is the while true first, and the while true has a huge importance because the while true means for a longer period of time first, and then it means also for wider set of users. So the testing team is 10 users, 100 users, or if you are really rich, you would pay 1,000 testers in a third world country, but it's still a small set of users. In production, it could be your millions or billions of users in parallel. So it's again orders of magnitude faster than testing.
That's a bit what they're doing in open source what's the phrase again? That all bugs are shallow in the...
and bugs are shallow with, I don't remember.
If you have enough eyeballs...
Exactly, it's the same thing. It's exactly the same thing. So,
but I still think this is not really anti-functional. The system should have an inbuilt capacity to learn. Now it's you who test it, even while in production, but you have to make it stronger afterwards.
Okay, but no, I see your point, and the answer is quite simple. So I'm working in software repair. So we are capable of creating patches with respect to errors. And so we change the software. So now if we inject errors and we repair them automatically, we somehow have a complete closed loop where the system gets better and better and better and better.
If you include yourself in the system.
No, if I take a fault injection system and I plug an automatic repair system together, you can have somehow an autonomous improvement.
How does the system work?
Well, it's basically we change the code automatically with respect to certain codes.
You can automatically change the codes?
Yeah.
How do you know, how does the system know what to change? you need to analyze the bug somehow.
There are many techniques, but somehow you need an oracle that you need to the bug, and based on this oracle, you change the code.
And that can be done automatically.
This is my main field of research.
And it is,
So you think the key definition of antifragile is the autonomy of the system?
well, the definition of antifragile is a system that gets stronger by being subjected to perturbation. It means it's the system itself. It's not somebody who corrects the system after the system has been forced to be perturbed.
It's internal all generated.
That's what your immune system does. It learns on its own to recognize certain bacteria, for example, and it's producing its own the antibodies fight those bacteria the next time it gets them.
It's adaptive.
Yeah.
And what's the difference between the concept of anti-fragile and a complex adaptive system? Because to me, you know, a complex adaptive system is a
Well,
system that can
anti-fragility, I would say, is a
react
stronger
perfectly.
aspect of complex adaptive systems. Complex adaptive systems normally are to some degree anti-fragile, but here you pick out this one property and you kind of magnify it. Saying it should become stronger by being subjected to perturbations rather than weaker. Most engineered systems become weaker in their perturbations. I mean, if I batter that table, it may survive, but it will be somewhat less strong than before it was battered. Well, if I fight with you, maybe you will get stronger by fighting with me.
Maybe I'll hurt my leg again.
Have you looked at these proposals to build the equivalent of an artificial immune system in software where you work with the idea of self, non-self? Whenever some piece of code appears that is not recognized as part of what the normal thing is, then it kind of automatically creates antibodies until it's proven that the code is inaccurate. Because it's a similar concept.
I know this literature. And
for computer viruses, that seems kind of a logical way, but I don't know whether it would work with bugs.
Yeah, it was actually so this famous paper on the sense of self for software, for new systems by Stephanie Forrest and so Stephanie Forrest is actually one of the inventors of automatic repair. So we are clearly the same line of thought and research, and they are actually the same people at some point working on this. So it's definitely related. Many ideas coming from there. Yes. And Stephanie Forrest will do many contributions in the future as in the past.
Yeah, so you don't see these as two different technologies.
No,
you
it's the
expect
same.
that they will merge at some stage.
The same concept of rules and same techniques. But again, the key missing here is to do this in production. This is the key.
But I think one of the things we could profit from, as I said, is on the one hand the perturbation model, trying to understand more clearly how you can generate perturbations that are as diverse as possible and as unexpected as possible, while still being somehow realistic, creating something that is so unlikely ever to happen.
Exactly.
And for that you can maybe use some principles from complexity science. For example, I'm just saying power rules. Let's say somebody who makes a random generator typically samples the whole space evenly, or use some kind of a Gaussian curve. A power law is a different kind of distribution. So the power law might, for example, say that there are lots of small perturbations, but from time to time there are very big ones. Like lots of servers that break down at the same time.
The chaos gorilla is done. Yeah, definitely. I think you perfectly the one of the three main requirements: diverse, unexpected, and unrealistic.
No, yeah,
If you have this, well, just it's fine.
And another problem I know that is a problem of resilience is the what's the name, the cascading failures. the idea that certain systems you have a kind of a positive feedback, and if one thing goes wrong, then more and more things go wrong, like the example you gave with the Google Doc plugin, which crashed the browser, which crashed the whole environment. It would be good if you could find out systems that have this property where there is a propagation of failure, so as to shut down. Because one of the techniques against that is to create what they call firewalls, like places where a typical failure will not be able to propagate. So you kind of encapsulate, for example, the browser is sufficiently separate from the rest of the environment so that whatever goes on in the browser does not affect the rest of the environment. It would be good to be able to test for that specifically.
This one is very easy because most software systems are fragile systems. In most software systems, there are error propagation that go much further than they should go, as this example.
Which is kind of strange because I thought that software was always kind of developed in an object-oriented way, meaning that you try to make modules that are as independent as possible.
Well, again, so there are this notion of independence, but the way we realize it typically in software is not independence with respect to the error propagation. Again, and to me there is this is a problem of education and mindset. And so you're right. So this is something that we discovered, that is taught, but not with respect to fault propagation. It's not with respect to order and architecture and such.
So the modularity in software development would not really be modularity in terms of errors.
Exactly. So ideally, the ideal modularity concept in software development is a modularity concept for both the maintenance, whether it's easy to change the program when you change only one module, and it's also a modularity concept with respect to isolation and encapsulation with respect to others. Some realization of modules, of modularity, somehow go in this direction, but it's absolutely not the case, not the majority. Absolutely not the majority.
No, because this example you gave with the Google Doc plugin there, it was very obvious that these should be different modules. Still they catch each other.
What is the reason for that? Why do you think? Because it seems, at least from what I know from Java, I mean, you have all the technical sort of capabilities to do all these how is it called, catching errors, etc. in all the objects. Exceptions, yeah, exactly. So why isn't it done? I mean, just because people, I mean, it's a lot of work, additional, or there is a better reason for that?
To me, there are two reasons. The first one is because people don't do it, they should do. But the second one, especially in Java, I work all our experience in Java, is that by default, the modularity concept in Java, which are classes, packages, class loaders, etc., they don't encapsulate the errors and the error propagation. So, for instance, if you call an example of try-catch, there should be a default try-catch at the level of package, let's say. Which means that you would ensure that there is never a propagation behind the module boundary, across the module boundary. And it's not the case. The system has not been designed this way at all.
But it's usually because of assumption. If I use a class, let's say that you're a class and I am a class, and I need a service that you provide, and I ask you, Martin, could you please pass me the box? You give me the box. And it might be that the box has a time bomb. I don't know, let's say the time bomb is the exception. I just want to use it and I open it and it explodes. It's because I assume it is the normal case. And you cannot always assume, you cannot be testing every time you ask to another object for, is it the right thing?
I see your point, I agree with you, it's a matter of assumptions. But again, I think that the key assumptions behind the modularity concepts used in 99% of software are not the correct one. With respect to errors, again, they may be really good with respect to development from the human side, but they might be really bad with respect to errors and isolation. So I completely agree with you. It has something to do with assumptions. It's completely defined by assumptions. What are the key assumptions behind the software concepts we use?
If maybe a stupid example, typical problem is dividing by 0, you get an infinite value. Would some module give that infinite value to another module and the other module would accept it and not crash?
So in this example, there are many solutions, such as instead of throwing an exception, so stopping everything, it would be passing an infinite value. It's called not a number value, also in certain software stacks. It could also be returning 1 instead of infinite. I know that from a mathematical viewpoint, it should be infinite. But from a pragmatic viewpoint, if you try to divide by 0, you return 1 or 0, I don't know. But something that's better than an exception that breaks everything, including, for instance, an Ariane 5 rocket. The Ariane 5 rocket, typical example of fragility, it's exactly the same thing.
Was it because of the division by 0?
It's almost the same thing as division by 0. It was only that you had a number stored on 64 bits, and it had to be transformed into a number stored on 32 bits, smaller scale. And this was impossible exception. And we lost billions of francs and Deutschmarks at this time, because there are clearly many. In this case, we could have just approximate the number after, and it would have worked just fine. You have lost a little bit of precision. Maybe we would have to reboot the rocket at some point, but that's it.
It's a very expensive software mistake. And then the other thing I think it's important is to find a measure of resilience. And I have been brainstorming a little bit about it. Resilience is well defined in ecosystems, and there they use models of dynamical systems with attractors and basins. And as long as the system stays in the basin, it will go back to the attractor. So if you perturb it, you push it out of the attractor where it should be, it goes into the basin. As long as it's in the basin, it will go back to the attractor. If you push it too far, it ends up in the basin of a different attractor, and it goes to a completely different state. So that's what you don't want. So one measure of resilience is, for example, the size of the basin of attraction. So you want to have that size as big as possible so that you can push the system in all possible direction, it will always come back. And I wonder, it's not obvious to generalize it to a discrete binary system like a software system. But I wonder whether you wouldn't be able to formulate a similar kind of model, I think it's called the latitude. The latitude aspect of resilience is how far you can push it away from its state and it still comes back. So there is another aspect which is, if you imagine an attractor basin as a valley, is how deep the valley is, how hard you have to push to get it out. And there's a third one, that is that if the basin is not equal, it might be that you are actually very close to one border, and here you have plenty of space to be perturbed, but here a single perturbation will push you out. And that was called the precariousness aspect. So they had three aspects: resistance, latitude, and precariousness, to kind of give a more precise definition of what's resilience. So it would be worth thinking about concepts like this to develop this measure of resilience, which would then be a measure of your gain. Because if you increase, for example, the latitude or the precarious, or you reduce the precariousness, or you increase the resistance, that would be one way to say, I have improved the system that much.
To me, here you are at the level of the perturbation level. It's whether you push the system very far from the initial state or not, whether you push it in 1 millisecond or 10 seconds. It's more at the level of the perturbation level here. But again, since the perturbation...
So the perturbation model can be used as a model to estimate how resilient the system is. And then you can say, by catching this particular problem and solving it, I have increased the basin in which I can move, so I have a gain of that much some kind of a measure. So actually the two are connected, the perturbation model and the perturbation game could be connected.
Exactly.
If you define this kind of ideal state and the basin of, or what you call the envelope of acceptability, I suppose it's similar to the base.
It's related. It's definitely related. It's definitely related.
If you can increase the envelope of acceptability by catching a particular mistake, you have increased the resilience of the system, and you can say how much you have increased it because you know how much you have increased the envelope.
Yeah. So thank you very much.